We'll begin with the external free body diagram of this beam. We're not told the thickness. It's going to turn out not to matter for this example. We have a distributed load acting on the bottom of the beam. With an intensity of 300 newtons per meter. And we know that we have a point D, we have a point B, point A. Point A, we have a pin, which will mean we have an AX and an AY. And we have a rope that goes from D over a pulley back down to B. So it's one continuous rope. So when it's in static equilibrium, the tension in the rope is constant. So we'll have some tension pulling up at B, and then that same tension pulling at a 45-degree angle at point D. For the picture, I'm going to leave the distributed load as a distributed load. Like we talked about when we first talked about distributed loads, externally, we can simplify this down to just a point load, and we can run all of our analysis that way. However, if we do that, that's good externally, but internally, we can't make that simplification right off the bat. We need to keep it as a distributed load. So I recommend keeping it this way, or else we could forget that it was originally a distributed load, and that affects the pictures we're going to draw downstream. From the external picture, there are three unknowns here, AY, AX, and T, so we can solve this with our equilibrium equations. We'll start by summing the moments around A. That way we can get our tension right away. Around A, there's going to be a moment due to this tension at B. So we'll have 6 times T. There will be a component from the vertical, a contribution from the vertical component of the middle tension at D. That will be T sine 45 times its distance from A, which is 3. Also going to be positive. And then what will the moment caused by the distributed load be? Right, 1800 times 3, so that comes at this step. This is where you can simplify it. So remember, we can simplify this externally, which is what we're doing now, to one point load that acts at the center of the distributed load, since it's a rectangularly distributed load. So its intensity times 6 is 1800 newtons. And it's equivalently from A, 3 meters away. So that's just kind of for our recognition. That's going to be then a negative 1800 times 3. I don't actually want it in my free body diagram, though, or I'm double counting this distributed load. So equivalent force of 1800 newtons acting 3 meters away from point A. From the first equation, therefore, we know the tension is 660 newtons. Now, looking in the x direction, we'll have AX plus T cosine 45. We just found what the tension is, so we can find the value of AX. The value of AX, negative 470 newtons. And the y direction will have AY minus the 1800 from the distributed load, plus T sine 45. Again, we know that T is 660 newtons. Solving this for AY, we get that AY also is 660 newtons. Now, we're interested in finding the internal reactions at E and at F. And we're going to take vertical cuts here, or transverse cuts to the beam to do that. We'll get into the other types of cuts later. Let's begin at E. We don't have to worry here if we're just to the left of E or just to the right of E. We only have to worry about that if there's a point load or an applied point couple on the point that we're studying. E has no point load or point couple. There is a distributed load, which we have to account for, but that won't change if we're just to the left or just to the right of E. The method we take is we'll make a vertical cut through the beam, or a cut transverse to the beam that crosses through E, and we have the option of taking everything to one side of the cut or the other side of the cut and copying it exactly from the original picture. It looks like there is less going on to the left of the cut at E, so I'm going to choose to model that, although our answer will be the same no matter what whether we took the left side or the right side. So I'm going to copy exactly everything that was happening from A to E externally, and then where I made the cut, I have to model what were the loads keeping the material held together at point E. From the external picture, we know that at A, there was a pin reaction we discovered to the left of 470 newtons and vertically of 660 newtons. And also acting from A to E, the distributed load, only that much of it that touches from A to E. So this piece of the beam can only see that segment of the distributed load. The rest of it is reflected in the value we found for the pin at A, but in this picture it only knows that it goes up to here. It doesn't know what's going on in the rest of it. We do need to keep this, or it is a distributed load. We don't want to take our original picture, simplify it to the point load, and then use that picture to draw this, because if we did that in that beam, if we're cutting through E and keeping everything to the left, in the simplified picture, there is no load. It can't see the distributed load. It's all right here. So that's why we always have to go back to that original picture and cut through it. And now in that picture, we see that some of the distributed load was acting on the beam from A to E. Once it's in this picture, now we can simplify it down to a point load that will be easier to work with. So the equivalent point load from that distributed load is going to be the 300 newtons per meter times 1.5. So equivalent of 450 newtons that comes from the distributed load and acting at the middle, since it is a uniformly distributed load. So the distributed load I did in this picture just simplified to the point load, and it will give me the right answer within this picture. And then where I cut through the material at point E, I'm now going to have that internal normal force I'm going to call P sub E. I'm always going to draw it coming out from the surface of the cut and always orthogonal to that surface. I will have a shear force. I'm going to assume that it's up. That V sub E. And an internal moment, internal bending moment, I'll call M sub E. And I'm going to assume that that is counterclockwise. For beams, I will go over the standard convention. For this class, I don't care too much about it. But in a beam, it's standard convention, depending on the direction, which side we're cutting on, that these are the assumptions we make about the moment and the shear force. So if it's a cut on the right side of the beam, we always would make the assumption that the moment is counterclockwise and the shear force is up. And if we're cutting on the other side, like we'll see in our next picture, we would always assume clockwise moment and downward shear force. If you want to use this convention for this class, that's fine. I'm not going to enforce it for this class. Once we get into EMCH 213, these assumptions are important when we're looking at beam bending. We have to know what is the assumed value, if it's positive or negative, so that we can interpret that positive or negative to be what direction it is.
Is that because you have to have, if you cut it on the one side, it's, you have to counterbalance equal and opposite reactions?
Right, so if we drew both of them side by side, then on this side it would look like that, and then it would look like that, and that. So that way when they come back together, they're all equal and opposite, and they add up together. But this particular convention is important once we get to beam bending, because if we have positive values for the moment and positive values for the shear, those will influence, is our beam bending upward or is the beam bending downward? And that's where the equations we're going to use depend on this sign convention so that we can interpret, is our deflection up or is our deflection down? So for this class, it's not as important. We'll enforce it in 213. Introduce three unknowns that we'll be able to solve for. Continuing from the other day, this will be equation 4. If I sum forces in the x direction in my picture E, from the pin I have a negative 470 plus the internal normal force. At point E, the internal normal force, 470 newtons. Internal normal forces we can interpret as being tension or compression. So by our assumption of coming out from the surface of the cut, a positive will always mean tension, a negative will always mean compression. We don't have this same interpretation for the shear force. We don't have the same interpretation for the bending moment. It's just the normal force that can be in tension or compression. In the y direction, we have from the pin, the 660 up. From the distributed load simplified down, we have a 450 down. And by my assumption, we have VE up. At point E, the internal shear force, by my assumption, is negative 210 newtons. I'm not writing compression here. Shear forces don't have that interpretation. Only the normal force does. And finally, the moment around E. I'm making the assumption here that the centroid is at the center of the beam. That might not be the case. So I'm going to assume that the line of action of the 470 newtons does pass through the centroid. Even if that were not true, I don't know what the cross-section actually looks like. If the centroid were actually down here, this distance is going to be usually very, very small compared to like this distance is going to be. So if I did take into account the moment that this pin caused around the centroid, relatively it would be very small compared to the moment caused by the forces like this one is 1.5 meters away. This distance might only be like a couple of millimeters. So usually I'm going to be ignoring or assuming that just all of those lines of action pass through that. So when I take the sum of moments, I'm going to say the 470 newtons does not contribute to the sum of moments around point E. Again, point E specifically being the centroid of the beam. So PE does not contribute, VE does not contribute. I'm assuming the 470 contribution is 0 or negligible. So what does contribute? I have the internal bending moment, which I need to solve for, M sub E. I have, from the distributed load, a force of 450 pounds, a distance 0.75 meters away, and counterclockwise around point E, and minus 660 times 1.5. So the internal bending moment at point E is a positive 652. This is in Newton meters. Again, at F, there's no point load. There's no applied moment on F, so there's no F to the left or F to the right. So cutting through F, again, we have the option. Do we want to take everything to the right or everything to the left? There's less going on to the right-hand side of F, so I would recommend make the cut at F and keep everything to the right. So acting on that segment, we're going to have the tension in the rope at B. We have the distributed load that goes from F to B, which again we can simplify down to that point load located in the middle. And on the cut surface, we're now going to have P sub F. I'll assume VF down, and I'll assume MF clockwise. Counterclockwise. I'll reiterate, the normal force has nothing to, our assumption of the direction of the internal normal force has nothing to do with the global coordinate system that we chose. It only matters that it's the outward normal from the surface of the cut. So even though it's pointing in what we establish as the negative x direction, this is still a positive, we're assuming a positive internal normal force. When we go to write the equations, that's where this coordinate system is going to be taken into account. As we'll see in our seventh equation, if we sum forces in the x in picture F, even though we are assuming that it's a positive internal normal force, according to our coordinate system, it does point to the left. So it is a negative PF in this equation. In this picture, it is the only force acting along the x direction. So we know that the internal normal force at F is now 0. At E, it was 470. It's dropped to 0 by the time we get to point F. In the Y, we have the tension in the rope up. We have the distributed load down. And by my assumption, we have the internal shear force down. So at point F, we get positive, by this assumption, positive 210 newtons for the internal shear force. Same magnitude, but the sign actually does flip. And finally, taking the sum of moments around, I'll take point F. I have a negative m sub f, assuming clockwise direction for mf, minus 450 times 0.75, plus 660 times 1.5. My internal bending moment is going to be, again, a positive 652 Newton meters.